Hi, Mr. D here, and with another math-tastic video. Check it out. We are looking tonight at limits at infinity, and these happen to be functions with two horizontal asymptotes. So we've got some function going on where we've got a horizontal asymptote above and below the curve. So the curve maybe is oscillating a little bit between the two, or doing something to where we have two asymptotes, okay? So where does this happen? This happens with functions with radicals in the numerator or denominator. Now, most of the time, if we were to graph these functions, we would say that if I was looking at my x-y axis like this, we would say that as the function goes off to infinity, it is doing something perhaps like this. And so when we look at those asymptotes, then we will place them here and here. So many times that's the situation that we're looking at with some of these functions. So in this case, we have radicals in either the numerator or the denominator. And how do we get rid of those? What are some strategies that we can use in calculus to avoid the pitfalls of falling into everything is just zero, right? So what we want to look for is we want to divide the numerator and the denominator by the same power of x if possible. If the function has a numerator and denominator without a radical, then we might want to try and divide everything by the higher power, so that will reduce the one with the lower power. Remember, back in another video we explained that there was the difference between, one of the theorems was if you had a constant over an x, if that x continued to go to infinity, then that number would get decreasingly small and small and small. So if we keep taking half of a number, we can see that if you're this big and you go half as much and then half as much and then half as much and then half as much and half as much, pretty soon you're going to be so close to zero it's arbitrary. So one of the strategies is then to divide the numerator and by the denominator by the same value. And we also have to recognize that if we have some nth root of x to the same nth power, then what you get out is just an x. Okay, so in that case, within the function, the x's will cancel, and that's what we want. It's really the multiplicative inverse that helps them cancel, but we don't need to go into that property right now. So let's look at an example here where we have a situation where we've got a radical in the denominator, and we are being asked to find the limit as x goes to infinity. So here we go. Example number 1 says, if we have, scoot this over a bit, if we have a function that's 3x minus 2 divided by 2x squared plus 1 in the denominator under a radical, and we let the square root of x squared equal x. Well, that's true, right? If I take the square root of something squared, you just get the number back out. We want to divide the numerator and the denominator by that same piece. So in the numerator it will be by x, and in the denominator it will be the square root of x squared. Now that works because I can multiply radicals within radicals. Okay? If I don't have a radical, then I can't just arbitrarily put it inside the radical, if you will. So what we have to do is we have to create the radical to the sense of this. If this were an x to the 4th, then I'd want to create a radical of x to the 8th, because now this is a x to the 4th inside, so my outside might be x to the 8th. This is a square root of an x squared, which gives me an x, so it's the same thing. So here's what we've done. Notation-wise, I just left the limit out for now, but that's okay. I'm going to divide the numerator by, and I went ahead and split these apart just so we could see, because it's a fraction. I can split them up as long as I have the same denominator. So we get 3x over x minus 2 over x, and 2x squared over x squared plus 1 over x squared. And again, I can do this because I am multiplying by or dividing here, excuse me, I'm dividing the numerator and dividing the denominator by 1 over x, or x square root of x squared. So now, what happens is, what you'll notice is this x and this x will go away, right? So these x's will cancel. That's what we want, and that becomes 3. This x will remain, so I leave that as 2 over x. Under the radical, x squared divided by x squared, well, those cancel, and we're left with just 2, and then 1 plus 1 over x squared, which gives me in the denominator 2 plus 1 over x squared. Well, now I bring in the limit. As the limit goes to infinity, this value right here, well, as this x increases, right, the value of 2 gets decreased massively. In the denominator, the same way. 1 over x squared. If I keep squaring a number big, this number grows without bound, and 2 remains itself, so this will automatically go to 0 as well. And again, if you think about it, 1 over 1 is 1, but 1 over 5 is 1/5, 1/10, 1/100th. The values in the decimal places are getting so small that they become arbitrary and close to 0. Negligible at that point. So then as we take the limit, we are left with 3 over radical 2, which is the answer for this. Now, another way to think about this is, and this comes up in our class sometimes, is what happens if we were going to negative infinity? You know, what would be the result? Well, now I have to take the negative side as I go over here, as I'm looking at this graph. Now I'm looking at the negative side, and so should get a negative result. So if we were looking at going to negative infinity here, then I would want to change this so that the negative is on the outside of the radical, because I'm going to be multiplying by the negative of square root of x squared. Okay. So let's look at an example of that now, since you asked. All right, here we go. Example number 2: the limit as x goes to negative infinity of x over x squared minus x. Again, in a simplified version, I've just simply noted that the square root of x squared is x, so x divided by x. And then now, again, we add in this negative to the outside because I'm going to, in the negative case, so I need to end up with a negative y value. And x squared over x squared becomes 1 minus x over x squared. So the simplified version, again, these cancel, that becomes 1. And we're left with x squared over x squared, which is 1 minus x, 1 over x. And again, as this x grows to negative infinity, then that goes to 0. And we're left with 1 over the square root of 1. And then don't forget your negative out here. So we get as a result negative 1. All right, final one. Okay, what happens if we have something that don't match? So we've got x values that don't match. The exponential powers don't match. Square root of x to the 4th minus 1 divided by x cubed minus 1. Well, what I'm going to do is I'm going to choose and divide everything by x cubed, and within just the radical itself, I'm just going to divide what's in the radical by the x cubed, and not try and get inside the radical like we've done before. So if I do this, we divide both the numerator and denominator by the same x to the nth power. So again, I'm going to divide this numerator by an x cubed. And I want that because I know in the denominator I'm going to get it to cancel out. So this stays the same. Now, come down here. Well, these cancel. X cubes go to 1, right? So that goes to 1. Minus, well, this is going to go to 0. So that goes to 0, right? Because the x cubed in the denominator. So we're left with 1 in the denominator minus 0. And in the numerator, well, think about this. if this x cubed continues to grow and grow and grow and grow, it won't matter what this value is. This is just some number, right? So as long as this grows, then this value will diminish so far that this whole thing actually goes to 0 because it's in the denominator, and so that will all go to 0. So we're left with 0 over 1, or the limit as x goes to infinity for this function will go to 0. All right. Thanks again. Hope you've enjoyed a little math today with d Dijkstra and today's limits at infinity, where you might have a function with 2 horizontal asymptotes. Good times. All right. Peace. Have a great night. Bye.